So parameter file, a single text file, which is included in the simulation. It includes all parameters of interest, so allows you to essentially, okay, this is what I'm going to change. I want to put that. Anything you want to change, you put it in the parameter file. Okay. Convenient way to organize your design and important parameters, and convenient way to change parameters read on analysis. That's the importance of the parameter file. And we'll show you all of this in real time. So bear with me for a few minutes as we go through this background. This is an example of the parameter file. Hard to see, perhaps. Here, basically you can write comments on the top. For example, here we are modeling a, I don't know whether you can see it on your, in your book. Yeah, you may be able to see it in your book. So we have defined, here is on the top, we have the back EMF constant defined, and we defined A as a constant here. We have got also a rise time, fall time. So rise time, fall time, this is for the back EMF. 1 by frequency by 12, which is basically 30 degrees. You have got pulse width, which is 1 by frequency by 3, right? R motor, which is 181 milliohms. The inductance of the motor is 242 microhenries. And then delay 1, here you can see, is 30 degrees. 1 by frequency by 12 is 30 degrees, right? That's time by 12, so that's 30 degrees. And then delay 2 is delay 1 plus 1 by frequency by 2. So delay 2 is 180 degrees with delay 1, right? And delay 3 is delay 1 plus 120 degrees. So we have built 6 delays that way, which we use extensively during simulation. And then you also have a gate TR. This is mainly for generating the square wave, 10 microsecond TR, 10, and this is probably too much. It should be 1 microsecond. But then, if you're trying to speed up your simulation, this has to be bigger. If you make it 1 microsecond, then you reduce your simulation step to smaller than 1 microsecond, because otherwise you'll have inaccurate results. Gate drive voltage 5 volts, and then we have some type 1 amplifier parameters, which we can ignore for the time being. Don't pay any attention to this. And then the PWM parameters. And I'll show you, this is a very interesting PWM function, which I like a lot, because it is a whole lot more simpler and robust than what we have used before. So PWM generation, we can set the high and low, and then PWM frequency and the gain, which helps us with the convergence. Gain, and I'll explain that in a minute also what the gain means. And then we have got limiter block, 0.95 and 0.05. Now, the limiter block is more of a practical insertion than a theoretical one, because in real life, if you don't have limiter block, you run into shoot-through issue. So if, let's say, if I put this limiter block, let's say, to even at 0.99, and if I'm running at very high speed, very high frequency, let's say even 20 kilohertz, then this may not give me enough time to, when I transition, when this becomes very small, then if these are complementary drives, I don't have enough time, I may not have enough time left, let's say when I want to turn this off and turn this on. The controller may demand 0.1 microsecond. I want a transition between 0.1 microsecond, right? So the top guy tries to switch off, the bottom guy tries to switch on, and you have issues. Now, of course, you can put delays in there, you know, the dead time delays and all that good stuff is there. But even then, that delay you want to reduce, because if you're trying to maximize your voltage to your drive, you want to minimize that delay, right? So there are practical issues why you want to include this limiter block to simulate somewhat of a realistic.
Is it duty cycle limiter?
Yes.
But how is it going to help the shoot?
Good question. Let's see. We have. See, if I have a complementary drive, right, and I have, let's say, the dead time between the two, if I take an IR driver, international rectifier driver, I can have a dead time, let's say, about 500 nanoseconds, right? So if I have a MOSFET, so when I'm going to, let's say, 0.99, right? Let's see. Here. So this is my PWM. So theoretically, if I go to 1, right, my top switch is on, and the bottom switch doesn't matter, right? So that's
Normally independent.
Pardon me?
Right now these are independent because they're considering only high side figure.
That's right. That's right. That's right. The more important of this is to really include when you have a complementary drivers, right? That's more important.
It doesn't have any significance as of for this high side PWM because as you said high side PWM only the top switches you are going to do PWM. In the bottom you are going to leave them a square.
That's correct.
So,
that is correct.
This in this case this particular thing PWM whatever you are doing is it only for AT, BT and CT.
That's correct.
Not for the bottom. So
That's right. But I think also there's another implication. I can never have I never want to have my top switch off. Because if I want to have my top switch off, okay, I can accidentally go into a linear mode of operation for the top switch, right? So let's say I am, this is my PWM waveform, and this is my duty cycle command. Now, as it approaches 1, I'm trying to, the gate drive pulses are going like this. And they become very, very tiny. Now, when they become very, very tiny, I run the risk of blowing the top back because I may not have enough time to turn it on, right? So if I have, let's say, a pulse which is 500 nanoseconds, and obviously if you're using an IGBT, you're toast, right? You can't turn it on very fast. So that's where I think it becomes significant even for practical reasons to have the limiter block even in this case. Does that make sense?
basically what you are going to do is you are going to on the width of the pulse you are going to make it a little bit higher.
That's right.
You are increasing so that the IGBT reacts. Before the IGBT reacts, it's going to turn off. So you don't want that to happen.
Right. I want to make sure that we remain in the switching operation zone. We never run a risk of running into a linear operation zone where IGBT becomes a resistor or a MOSFET, as a matter of fact, becomes a resistor.
Basically, you are limiting the width of the pulse.
That's right. Basically, that's what you're doing. That's exactly what you're doing, is limiting the
width of the smaller pulse.
That's right. That's right. So that's why it becomes very, very, very critical as you increase the even at lower frequency, you want to have that limiter block.
What will be the percentage from the peak value which you see?
So it really depends on the device you use. For example, if I use a MOSFET, let's say from IR, I use a MOSFET, low voltage MOSFET, let's say 60 volt, even 100 amp MOSFET, I can switch in nanoseconds. Let's say, but at least that's what the data sheet says. The data sheet says that I can switch in nanoseconds. I can have, let's say, 200 nanosecond switch of time. But I want I want at least some safety margin. So I can say, well, let's say it's 1 microsecond. I don't want to get near 1 microsecond. So if you're switching at 20 kilohertz, right, that is 50 microseconds. Then one microsecond or 50 microsecond is 2%. So you could set that. Say, okay, let me set it at 0.98 and 0.02. So that's one way to think about it. Right. So that's the thinking behind the limiter block. It's from having burned few MOSFETs.
So you're putting it at 0.01 to 0.99.
Right.
So you don't want to go into overmodulation.
That's right. Now, overmodulation, I think, is we'll talk about that in AC inverters where you have low frequency, and you do run a risk if you when you're transitioning, your pulses become too small. You can get hoarse. Okay. So let's see. Any other questions? All right. We have this. We talked about the gate drive. We talked about this. We talked about this. Okay. And let's see. Now here is just highlighting the motor parameters. If anyone would like to have a data sheet of BNT23 motor, just email me and I'll email you the data sheet so you can see how we incorporated the parameters. So BN23 is the motor model we have incorporated, and then we have taken the frequency as that, and then these are the parameters related to, some of the parameters related to the motor.
Why do you want to have PWM there? Just go back to the earlier sheet. Motor parameter.
Okay. So the way this PWM is generated is that we're taking a cost function. Okay, we're taking a cost function, and then we're doing a cost inverse 1 by pi. That's how we generate the triangle. So this one basically is 0 to 180 degree ramp up. Okay, 0 to 1. So count up, count down, right? So we take the cost function 2 pi ft. So basically f is your PWM frequency, right? And basically this is a sine function with plus pi by 2. And we take a cos inverse 1 by pi. So basically this 0 to 1 is 180 degree run up, count down, right? And then we take tan hyperbolic function, and we have high as a parameter, low as a parameter, and high minus low by 2 plus high minus low by 2. That's how we actually derive these pulses. Because parameter hyperbolic function saturates, so we are able to use to our advantage. Now, I have an Excel sheet which I can show you. It's easy to write this in an Excel sheet and see how it works. And the good part is that you can actually manipulate high and low very easily. So if I want to set high and low, we can set that up very easily. Now there's a gain G here. So that defines roundness of these pulses. So if you make G higher, these become more square. And if you lower the G, these become round. So if you're running into convergence issues, then you can use this G number to smooth out some of the convergence issues. So let me just show you the Excel sheet. So essentially, So you have, here is a switching frequency, then you have an A, which is essentially high minus low by 2, and B, which is high plus low by 2. And then you have the duty cycle command, and then this one here is your cos, A cos and cos functions. And this one here is your hyperbolic function, tan hyperbolic function. Now, so what you can see is we can have any, if you want 5 minus 5, then this is on the secondary axis is where the pulse width is. So you can see I can have minus 5 plus 5. And if I want to go, let's say 2 and minus 2, so it works for 2 and minus 2 as well, right? Sorry, 2 and minus 1, minus 2. And then if you want to go, let's say 2 and 0, it works that way as well. As you can see, that secondary axis changes. So you can see how it works. So that's what we have as a PWM generating station. Now, the only issue with this is that if your PWM frequency, let's say, is 20 kilohertz, 50 microsecond, then your simulation time step, we clamp it to be, let's say, 1/10 of the switching frequency. So okay, so if it's 50 microsecond, then I don't want, my maximum time step in simulation should not exceed 5 microseconds. Otherwise, you get inaccurate results on the PWM generation. That's the thing we have to, but that's needed anyhow. You know, normally you want to have, if you have a switching frequency of 50 microseconds, then if you're doing transient analysis, time analysis, then that's something you have to pay attention to, is what is the maximum time step for simulation. Okay, back to here. So I think we have seen this extensively, and then, all right, so after the model is built, we put a reference at 1, basically, which is about 3.25 amps of
Last slide I was not clear. Actually, we have a triangular signal, and this reference block itself will generate the PWM signal for you. Why we are using another equation to generate the PWM signal? We have a triangular signal, and this reference section and feedback section will give me this duty cycle set. So the comparison of the duty cycle setting with the triangular will give you the PWM signal, right?
Yes.
And what is the additional PWM signal we are using with the equations?
Okay, no, I think you're correct. You're correct. We just need a triangular signal.
Yes.
And what we have demonstrated is how we generate the triangular signal.
Yeah, triangular part I understood.
Right.
PWM part also we are generating with some equation. So PWM we have a triangular signal, and once we have a triangular signal and the duty cycle setting, the PWM is just a comparison between these two things.
Yeah, I think that, yeah, you're absolutely correct. That's one way we can do is use a comparator. So what you're saying is, essentially what you're saying is that why are we using another equation when you have this and you have the feedback signal? I compare the two
Exactly.
and I'm done.
Yeah.
Right? That's what you.
Simple as simple.
As simple as that. Yes. That you definitely can do that. You definitely can do that. Now here we have done it the way it is, essentially, so that we can control any convergence issues. We can control the way the PWM pulses rise or round off. Also, so it gives us better control. And also here, this block, all I have to do is the duty cycle command. Okay, so here, essentially I have a block, and I give a duty cycle command of 0 to 1. Okay? And I basically get pulses. Based on my duty cycle command, let's say if I did duty cycle of 0.5, I get 50% duty cycle pulses. Okay? So if I do 0.99, I have 99% duty cycle pulses. Now, this one is more useful block, as you will see when we use for large signal model. You know, we are able to use it quite for many other purposes. That's what I'm saying. But the concept you have illustrated is correct. You can the one way to do it is I have a feedback signal, and I can just if I have a triangular waveform, and you can as a matter of fact generate the triangular waveform using the V-pulse source, which we have used for back EMF and for gate logic. So that's definitely one way to implement that portion of the system. I think that's a very valid point. All right. So we here are some simulation results. Now I think the other point you could make is that you could also use simple PI block here, you know, which may be much more robust than actually using a amplifier when doing your initial simulation. Right? I can use a simple PI block. Here we have used a type 1 amplifier, which is very not necessary. You know, you can use KP and KI PI block, which would be much more robust initially when you're simulating initial setup. So here are some of the currents. So we have IA, IB, IC. The current waveforms look pretty decent. Okay, they look pretty decent, and